So I think hypothesis testing is very likely to come up on paper 3. It's been pretty light so far on paper 1 and paper 2. There are 9 hypothesis tests. Because it's paper 3, I think there'll be 2 of them. And I'm not going to go through all of the tests because I think 3 tests are the most likely ones to come up, but it could be anything, of course. And so make sure the null hypothesis is correct. You must identify the test first of all and make sure the null hypothesis is correct. Some of them are simply easy to identify. If it's talking about correlation, then it's obviously the regression t-test. The null hypothesis is rho equals 0 because that rho there is a Greek letter for R. So R is the correlation of whichever sample you've got. What is the correlation of the entire population? That's rho. And a null hypothesis is always a claim made about the population. And the claim is the neutral one. There's no correlation. If you want to get a sample and show me this correlation, then I may reject this. Okay, that's what a null hypothesis is. And you've got to be good at spotting them. Notice that all have an equal sign. They're written in symbols. Every symbol is a Greek symbol because it's referring to a population. And the only exception to that is P for the test of proportion for a binomial. And it's not a Greek symbol because the Greek symbol for P is pi. And it would look pretty weird if it said pi equals a sixth. And so that P there is talking about the population proportion. And just one word on that, because some students struggle with proportion. When we have a dice, when we roll it 60 times, we know that the probability of getting a 6 is 1/6. But what this is referring to is the population of rolls. That means if you took that dice and rolled it an infinite number of times, that's the population. It's the intrinsic population built into every dice. Now, if you did that, what proportion of all the numbers that you get out, those 6s, 5s, 4s, what proportion of those are 6? Well, I would expect on a fair dice for the proportion to be 1/6. Okay, that's why it's called that. Now, I think the 3 that are most likely to come up are the correlation one, regression, and the two sample ones, because they all basically look the same. And then on top of that are the chi-squareds that I think are also likely to come up. So I'm going to concentrate this video on just the correlation and the paired sample one. I've written a lot of videos about chi-squared. Watch them. I think that's got a really good chance of coming up. And the reason I think this is likely to come up on paper 3 is they can look identical. And you can, in fact, do 2 different tests on the same data. Which of these 4 is this data? And the simple answer is you can't tell me that. You have to read the question. It could be any one of the 4 of those. So the big 3 plus the relatively easy chi-squared goodness of fit. So you have to read the question. If this question is saying there's a bunch of runners who take this amount of time to run 400 meters or something. So this is like before. And then they do a month's training. And then they do the same run again. Then you'd say, which of these is it? Well, this would be the paired 2 sample because this letter A here is referring to a person. This is their time the first time they did it. This is their time the second time they did it. And so the method is you subtract them to get a D, the difference column, and then it's a 1 sample test. And the null hypothesis is that mu D equals 0. And you must write down what the meaning of this symbol is because it's not clear from here what it is. So you say, you write a D here and you subtract them. And then you say mu D is the mean, the population of all the differences, not just my sample of runners, but all runners in the world. If they were to do the training, would they improve? So that is one possibility. However, it could be a very similar scenario where we're saying we're going to test the runners. And then a week later, I want to test the runners again. And now they may have all improved, but is this a good test? Whatever test I'm doing, maybe it's some step-ups, and we're saying, how many can you do? Is that a good test? Well, it can be tested, the validity of it can be tested by running the same test again. That's called test retest. And if there's a correlation between them, then that is showing that this test is good, it's valid. Because the person who was best in the first test is best in the second test. And that's telling us the test is measuring something real. Whereas if it was all jumbled up and there was no correlation, then you say, well, what is this test telling us? We're getting different answers every time we do it. It's not valid. So that would be a test for regression. There's lots of ways the question could go to have regression, but that's the most subtle one. And remember that the null hypothesis is rho equals 0. Now, it could be that these are the test scores for people in my math set, or a sample of them. And here are the test scores for people in the other math set. And I am making the claim, oh, my set is doing better, which is obviously true. But we could test it. But now this person here isn't the same as that person there. These are just, is that 7 or 8 people from the other set, and here's the same number of people. It doesn't even have to be the same number. I could have that. Now, this is an unpaired sample, and so the null hypothesis is that you can write it this way, and it's quite nice because then it obeys the rules that it has an equals sign in, and like so many of them, that is equal to 0. Not all of them, but some of them, all of these. And lastly, of course, if that number was back in there, it could be a goodness of fit. This would be slightly unusual data that we'd have to have some kind of formula for working out expected values. So maybe these come from a Poisson distribution or something. But nevertheless, you could see a data table like this, and typically there'd be a few missing, and you'd have to calculate them. Maybe this comes from a normal distribution. The expected values depend on what the model is being used, and so they can come from any distribution or even just a probability on the syllabus. But nevertheless, it could be a goodness of fit. And then the null hypothesis is that. Okay, more videos to come.